So we will continue today working on the equilibrium of a rigid body. We were doing examples last time. We'll do another example. In the vertical pole DE, which is supported by cable DF, we have the following forces acting on it. We have that the tension in DF is equal to 150 kilonewton. The question is to find the reaction at the fixity. Okay, so here, if you look at your figure, they told you that E is a fixity, okay, because here you have the ground and DE is fixed to the ground, so you should know that it's a fixity. And you have the cable DF acting on it in addition to all of these forces, okay? So the external forces acting on our system will be DE plus AC, okay? It's one system. So the forces acting on it are the tension in cable and the 20 kilonewton forces at the different points. And we want to find what is the reaction at it. So what we will do, we will write the three equilibrium equation for a rigid body in 2 dimensions. Sum of x equals 0, sum of y equals 0, and sum of moment about any point you want equals to 0. Okay? To start with, the easiest equation will be which one here? What we can start with? In x, okay? We have that sum of fx equals to 0. Along x, we have only the reaction Ex and the projection of the 150 kilonewton force. So this 150 kilonewton, if we project it on x-axis, okay, you know that here we should find, to be able to do projection, we should find this angle theta, okay? So to find theta, if we look here at our figure, by geometry we can find theta, because tangent of theta is 4.5 over dE, and dE is 2.25 plus 3.75. Okay, so we can find the angle. Once we find the angle, we can say that the projection along x is 150 sine theta. Okay, so when we write sum of x equals 0, we have 150 sine theta minus Ex equals to 0. Okay, this is our first equation. Now, along y, we have that sum of Fy equals to 0. Along y, we have several forces. We have Ey minus, you have 20 kilonewton, 1, 2, 3, 4. So minus 4 times 20. And don't forget the projection of the 150 kilonewton force on y. So as you can see here, if you project it on y, it has a negative component. So we should do also minus 150 cosine theta. Okay, and this is equal to 0. Now these two equations will give us Ex and Ey. We still need to find the moment ME. For the moment ME, you are free to use any point you want, okay? But if by choosing point E, you will get rid of the moments of Ex and Ey, okay? So in order to find ME, we can do sum of moment about E equals to 0. And always remember at the beginning of your equation to set a positive direction, okay? So let's say if you choose the counterclockwise as positive, for example, then your equation will be plus ME, because we assume that ME is in the counterclockwise, plus ME. Now, what about the 20 kilonewton forces? The 20 kilonewton forces are producing a moment, all of these forces are producing a moment in the counterclockwise. So I will put plus. Now for the first force, it's plus 20 times this distance. This distance is 1.8. Okay. As you can see here, all all these parts are equal to 1.8. So for the first force, the distance is 1.8. For the second force, the distance is 2 times 1.8. For the third one, the distance to E is 3 times 1.8. And for the fourth one, the distance is 4 times 1.8. And all are producing a moment into the counterclockwise direction. So I will write plus ME plus 20 times 1.8 plus 20 times 3.6 plus 20 times 5.4 and plus 20 times 7.2. Okay, so now I still need only to add what? I still need only to add the moment of FDF, the 150 kilonewton force. Okay, so if I look at my figure, this is my force. I have two methods to find the moment of this force about E. Okay, or I divide it into two components. So the first strategy is to say I will divide it into X and Y. And I already found the XY component because the Y component will not produce a moment about EY because it's passing by point E, okay? While the X component will produce, as you can see here, if you take the right hand rule or if you do it with your pen like this, it is rotating into the clockwise direction about E, so it's a negative moment. And I will multiply by the distance, the perpendicular distance from E to the line of action of the force, which is 2.25 plus 3.75. Okay, so I should add to my equation minus the X component times 6, and the X component was 150 cosine theta. So it's minus 150 cosine theta times 6. Now, what is the other method to find this moment? The other method, if I don't want to decompose the force into two parts, what I will do, I can find the distance from E to the line of action of the force, this distance. So I do the perpendicular and I multiply the perpendicular by the force. Now, how to find the perpendicular distance? You have that this angle here is theta, okay? And you have that DE, the distance DE is known to be 6. So if I do the projection, what will be this distance? It will be D sine theta, okay? So here just when we replaced for the X component, it's D sine theta, okay? So if I do it by another method, I will obtain the same result because the projection, this distance is equal to D, which is 6 times sine theta. And then I multiply by the force, which is 150. So I end up with the same moment, okay? I will clear it to show it again. Look, if I want to find this distance, the projected distance, what should I do? I have that this angle here is theta, and I know that the distance here is 6. So I can write that the projected distance here, D, is equal to 6 times sine theta, okay? And the moment then, the moment of the force, the moment of the 150 kilonewton force will be equal to minus, because it's in the clockwise direction, minus 150 times the distance, which is 6 sine theta. So I obtained the same result I did previously, because previously what I did is that M150 is equal to the X component, so which is 150 sine theta times the distance, which was 6. So at the end, I will obtain the same result if I do any of the two methods. Okay. And now, once you replace in your equation, you can get the moment E. Any question on this?
دكتور here EX لا رايحة على left.
مش دي X مش على left، على right. Like this.
EX.
EX. Okay, look, because they assume that it is to the right, because if you look to your figure, the only force in X is the projection on 150. And to have equilibrium, EX should be opposing. This is why you should assume from the beginning that it is to the left. If you put it to the right, you will obtain a negative result. But it is fine, يعني. You can put it to the right, and then when you calculate, you get a negative result. But here, because it's very clear that it will be in towards the left, they put it from the beginning towards the left. Okay?
دكتور هون وقت استعملنا ال two methods for determining the moment تبعت the tension. One of which is negative, the second one is positive.
No, both are negative. Here, I should add the mine. Both are rotating clockwise, and you choose the counterclockwise, so both are negative, okay? So just add here minus. And the magnitude is the same, and of course the direction is the same. Both are rotating in the clockwise direction, okay? Okay, another problem. The 10 tons moving crane shown below has a mass center at point C. It carries a maximum loads of 18 tons. Find the smallest weight of counterweight C and also the largest distance D so that the crane doesn't tip clockwise when the maximum load is lifted, and the crane doesn't tip counterclockwise when there is no load. So, what are we talking about here? These structures are used to lift very high weights, okay? So if you look at this figure, you have, when we design this structure, we should pay attention, because sometimes we don't have here anything. If we put a zero load, if we don't have a load here, then what will happen? Under the effect of the counterweight, we can have the risk of tipping over. Tipping over which point? You know, we will lose contact with which point? Imagine that you don't have a load here. Yes, we will have rotation about A. Okay, so if zero load, I'll write here, if zero load, we have the risk of tipping about A. Okay, so we lose contact. So we lose contact with B. And the second critical case is what? If maximum load, if we have high load, if very high load, then we have the risk of tipping about which point? If you have here a very high load, it will try to turn now about B, okay? So we have the risk of tipping about B, and we lose contact with A. Okay, about B, and we lose contact with A. So what we will do together now, we will try to design the system in order to avoid these two critical scenarios. We don't want to, when we don't have load, we don't want to tip about A. And when we have the maximum load, we don't have to tip about B. Okay, so this is why first we will consider the first critical case. Okay, if you have a very high load of 18 tons, okay, because we said that our structure should support maximum 18 tons. So if I put the maximum load here, okay, I should just be at the critical case of the very high load. So for the very high load, we have a risk of tipping about B and losing contact with A. When I say that I lose contact with A, this means what? Can I have a reaction with A in this case if I lose contact with A?
No, no reaction.
No. This is why for the first critical scenario, I say that for this, if I reach this weight, then the reaction at A becomes 0 because I am at the moment where I will begin to lose contact with A. And for this case, okay, what are the forces acting on my system? I have the reaction at B. I have the weight, the counterweight here. I have the weight of the structure, and I have the weight of my load. Okay, so now if I want to find a certain relation between, I want to find a design for D and WC. Okay, I will write sum of moments about B because my only unknown here, yani RB is not known. So and all other forces are known. WC 10 tons for the WC is not known, but I want to find a relation for WC. So I want to find an equation including WC. And to get rid of RB, I will do sum of moments about B. Okay, so I will write my condition that sum of moments about B is equal to 0. And I will choose a positive direction. Okay, let us consider the positive direction as counterclockwise. And now if I look at my figure, first, WC is producing a counterclockwise moment about B. So it's a positive moment, plus WC times. To find the distance, okay, the distance I should multiply with is the following. This is RB. And I should multiply by the distance here, from this point to this one, from the weight to the force here. Okay, what is the distance from here to here? Look, you have that this is 4 feet here. Okay, and D is from C to this point. So here the remaining distance is half of 4, which is 2. So the distance between WC and B is D plus 2. Okay, so this distance here is half of the distance between A and B is 2. And I add to it D, I get WC times D plus 2. Now, what are the other forces acting on my system? I will just clear it so that you can see it. I have now the 10 tons force, which is producing a moment into the clockwise direction. So if you look here, the distance you should find is from RB, so from here, from point B to this force, which is this distance here. You should find this distance, okay? And this distance here is simply a 3 minus 2, okay? Because you have from here to here, it's 3, and from here to this point, it's 2. So the distance is 3 minus 2, it's 1. So it's minus 10 times 1. And I still have the moment of the 18 tons force. And here, the weight is producing a moment about B into also the clockwise direction. So it's minus. It's minus 18 times this distance, which is between B and the force. And as you can see, this distance is 15 minus this part, okay? Minus this part, which is 2. From here to here, okay, you have 2 feet. And from here to here, you have 15. So this distance will be, the distance you want is from here to here, is 15 minus 230, okay? So this is your equation. This equation involves two unknowns, WC and D. So you have found the first relation between the counterweight and the distance. Okay? Now we will try to find another relation between WC and D, in order to have two equations with two unknowns. Okay. The second condition will be when we don't have any load at this point. So as we said, we have two critical cases, maximum load and zero load. So the next step now is to do the analysis of the case where we don't have any load. So if we don't have any load here, if we have a zero load at this point, what will happen? As we said, now we will lose contact with B because the structure will try to tip over A. Okay, so in this case, our B is 0, and when doing sum of moment, we will choose A to cancel the moment of our A. So now, if we do sum of moment about A equals to 0, here we don't have any load anymore, it's 0. Okay, we have now the moment of the counterweight, so we should multiply the counterweight with the distance here. This is the line of action of the counterweight. We should multiply it by the distance from A to this point, which is D minus 2, okay? Because this is D, and the distance from here to A is 2, so the distance is D minus 2. Now, for the 10-ton force, it's producing a clockwise moment, so it's minus, and I should multiply by the distance from here, from this line, the line of action of from A, if you want, to the force, this distance. Okay, this distance is 3 plus 2, which is 5. So now I got a second relation between WC and D. Okay, so when I solve these two equations with two unknowns, I can get what are the counterweight value and the distance D, which will just prevent tipping over. Okay, so I have here these values will satisfy the critical condition, and I will not have tipping over in this case. Okay, any question on this?
Yes, doctor. Over here at A and B we have wheels, and that's why we only have perpendicular reactions.
Yes, at A and B we have rollers. Okay, this is why we have perpendicular reaction. We don't have a pins. You have like wheels, so wheels can slide. Okay?
Yes. Okay. Also for the weight, 10 tons is the mass or the weight of.
Look here. If you keep it in tons, you will obtain the WC in tons also. So sometimes this is a method. Sometimes they refer to the weight in terms of mass. So they mean that the weight corresponding to this mass. So it's fine if you keep it in ton. The result WC will be also in tons. And then if you want to get the force in Newton, you multiply the mass by G.
Okay, thank you.
Okay, so we still have the last part. The last part is very similar, just I want to give you what they did. So for the last part, they give you D. If D is fixed, if D is 2.5, and I want to find the range of weights for WC, then also I should write the two conditions. So here, in the previous questions, I didn't fix D. I should find D and WC to not have the critical conditions. Now, if I fix D, then I can have a range of weight I can use. The range of weight to use will depend on the two critical conditions. So I will choose the minimum weight to not have tipping over when I have zero load, and the maximum weight will correspond to the condition to not have a tipping over when I have a maximum load. Okay, so I will do the same work, but now D is given. Okay, and I will find two values of WC, one that is the minimum value and one that is the maximum value. The minimum value is obtained based on zero loads, and the maximum value is obtained based on maximum load. So if I write the sum of moment equation in the two critical cases, I will obtain that the minimum value of the counterweight is 4.2, and the maximum value is 100. So I can say that to be on the safe side, to not have tipping over, WC should be between 54.2 and 100. Okay? So now, we will introduce the concept of 2 and 3/4 members. Okay? And we will see that these concepts are very important because sometimes they will facilitate a lot the solution of our problem. First, what is the definition of a 2/4 member? When a member is subjected to no couple moments, and when forces are applied at only 2 points on the member, we will say that it is called a 2/4 member. And please pay attention to the condition. Okay? The first condition, no couple. I should not have a couple acting on it. So let's say I have a member like this, and only I don't have a couple on it. I have only 2 forces acting on it, one at A, for example, and one at B. If my system is in equilibrium, how should be these 2 forces?
Your opposite.
Very good. Why? Why that should be opposite? Not only opposite, what
To
also?
cancel.
Yes, to cancel. Very good. So the first condition, they should be opposite to cancel. And what is the second condition?
Equal.
What?
Equal.
Yes, okay. Equal and opposite. And what also? Look, I will give you an example. These are 2 equal and opposite forces. Will your system be in equilibrium in this case? Why it's not in equilibrium? Because the first condition of equilibrium is sum of forces equals 0. It is satisfied. But the second equation, which is sum of moments equals 0, is not satisfied because 2 opposing forces will give you a couple. Okay? So the condition to satisfy the 2 equilibrium conditions, which are sum of forces equals 0 and sum of moment equals 0, the 2 forces should be equal and collinear. They should be like this. They should be along the same line, because when they are along the same line, can they produce any moment in this case? No. And in this case, the 2 conditions of equilibrium will be satisfied. Sum of forces equals 0 and sum of moment equal to 0. And in the exam, the majority of you didn't respond well to this question. I said in the introduction of the course, I said you have 2 cases, particles and rigid body. The main difference is that for rigid body, you cannot neglect dimensions. So the condition for equilibrium of a rigid body is not only sum of forces equals 0, you have 2 conditions, sum of forces equals 0 and sum of moment equals 0. So now, here you can see some figures, okay? For example, I have whatever is the geometry of the body. If I have no couple acting on it, and I have only 2 forces applied at only 2 points, then I can say the condition is that when I find the resultant force at A and the resultant force at B, they should be collinear and equal and opposite. Okay, so FA should be equal to minus FB, and they should act along the same line. Okay, so this is a very important idea for 2/4 member, because whenever you have any shape, for example, if you look here, if you have this shape and I have only forces acting, of course I'm neglecting the weight in this case, so weight is neglected. If I have force acting along only 2 points, I can directly say that the 2 forces are collinear along IAB. Okay, and this is why, if you remember, we said for a weightless link, the force will be along the link. Why? Because when it's weightless, a weightless link, and no couple is exerted on it, then we can say that the forces along the weightless link should be along its line of action. Okay, so the link is a type of two-force member. Now, what about three-force members? When we say we have a three-force member, this means that the member is subjected only to three forces at three different points. Okay, so for example, in this figure, you can see three forces applied at A, C, and D. So in this case, we have conditions for equilibrium. We have two possibilities. Or the three forces pass by one point, or the three forces are parallel. Okay, so if they pass by one point, why they should pass by one point if they are not parallel? Who will tell me? If they are not parallel, why they should pass by the same point?
They won't produce moment.
About what?
So
Yes.
then
Very good. Yes. Look, if you have two forces like this, for example, okay, they will not pass by D. And you have a third force applied at D. So is it possible to have equilibrium in this case? No. Why? Because look here, when you do sum of moment about D, it will not be zero. Okay, so you always have here, if you take this example here, if you take this point, for this point, these two forces are passing by this point. Okay, so they are producing no moment about this point. However, the third force is not passing by the point, so it will produce a moment about it. So I don't have the condition of sum of moment equals zero. In order to ensure that sum of moment equals zero, the three forces should pass by the same point. In this case, if I do sum of moment about this point, I will get zero. This is why we say that if you have a three-force member, the three forces should pass by one point to ensure equilibrium of the rigid body. Okay? And if they are parallel, then they should be in a way to have sum of moment equal to zero. So the magnitude of these forces should be selected in a way to have sum of moment equal zero. In order to understand more how to use 2 and 3 4 members, we will take a small example and we will see how using the concept of two-force member will facilitate the solution. In this
Doctor, I have a question.
Yes.
In the three-force member, the three force should pass by the same point to ensure equilibrium.
Yes, to ensure that sum of moment is zero. Okay, because look, if you have that, if F1 and F3 pass by D and F2 doesn't pass by D, what will happen? Look, this is the example. If FD is not here, F2 for example, if F2 is here, okay, then when you do sum of moment about D, F1 and F3 will have a zero moment, while F2 will have a certain moment about D. So when you do sum of moment about D, you will not get zero, which will not satisfy the equilibrium condition. So equilibrium condition requires that sum of forces equals to zero and sum of moments also equals to zero. Okay, so here when you do, if the first pass by D, you will ensure that sum of moment about D is zero and you will satisfy the equilibrium condition. Okay. Okay, so let us continue with the problem. So here we have lever ABC is pin supported at A and connected to a short link BD as shown in the figure. If the weight of the members is negligible, determine the force of the pin at A. So here, what do we have? If you look at your figure, you have two members connected together. You have ABC member connected to BD member. Okay? Let us try to first consider the whole system. If I consider the whole system, if I don't divide it into parts, what are the external forces acting on it? First, at A you have a pin. This means that you have AX and AY. Okay? And at D also you have a pin. This means that you have dx and dy. So how many unknowns do you have here? If you consider this system, the whole system, you have 4 unknowns. And we know that in equilibrium of a rigid body in 2 dimensions, we can write maximum how many unknowns, how many equations, sorry. We can write 3 equations. So if we take the whole system, we only have 3 equations, but 4 unknowns, it will not work. We should try to do something else, okay? What we can try to do, we can divide into 2 parts. We can take ABC alone and BD alone, okay? Now, if we take BD alone, we can say directly what? BD is a 2-forced member. Why BD is a 2-forced member? Because if you look at BD, okay, since they didn't mention the weight, you can consider that they said the weight is negligible. The weight of the members is negligible, so no weight. And if I take BD member, I only have 2 forces, one acting at B, one acting at D. So what can I say now? I can say that BD is a 2-force member, okay? And because it's a 2-force member, what can I conclude? That the 2 forces should act along the same line. And what will be this line? It will be line BD, because they are collinear, and the first force passed by B and the second passed by D, so their line of action is BD. So by doing this small analysis on the 2-force member BD, I deduced that the force along it at B and D are along line BD. So now, if you take member ABC by principle of action reaction, okay, if you assume that here the force is up, then by action reaction, here the force will be downward. And directed along which line? Directed along BD. So now, if you take ABC, you don't have any more 4 unknowns. You have FB, AX, and AY. So now, when you take ABC, you have 3 unknowns, and you can write 3 equations. So using the concept of a 2-force member allowed you to reduce your number of unknowns. Okay, I will continue the problem in a second session.